Oh, hey, my name is JMcCulloch, and this is KI4 for EC 312, 332, and 342. The knowledge integration for this particular KI is the signal transmission in a radio system. We are going to be dealing with the transmitter side today. This is the basic schematic, very simplified. So this is basically your video and audio is coming into an amplifier that's going into a mixer, which we'll talk about later, which goes into another amplifier and comes out after going through a bandpass filter through the antenna and gets transmitted to the cell. So for the entire duration of this presentation, we're going to be assuming GSM. That's a specific type of cell phone technology. Right here we have all of the different EMF spectrums, all the way from UHF, SHF, and EHF. These are incredibly high. Mostly what we deal with is in the UHF and SHF range. For the ECE 312 portion, basically we're dealing with a voice band, and humans primarily speak from 300 hertz to about 3400 kilohertz, or that's at least what we hear. 3000 hertz, 3 kilohertz, has a wavelength of 100 kilometers. That's huge. That's from Fort Collins to Denver, roughly. So that's completely impractical. GSM, however, uses around 900 megahertz as the carrier frequency, which has a wavelength of 3.3 centimeters. So that's much more manageable. So from a modulation standpoint, GSM uses GMSK, which is Gaussian minimum shift keying, which is a continuous phase frequency shifting, meaning as the phase goes in the continuous cycle, the processor is determining which bit we are dealing with depending on the amplitude of the frequency or of the phase at that point. All the way around, what we've seen plenty of times is the imaginary circle. So as our frequency is pushed into the system, it is then put onto a carrier frequency, which is the 900 megahertz from GSM. So that center frequency is going to be centered around F0. And this graph shows the general shape of the filter that we need to use in order to filter out all of the noise and all of the frequencies we do not want from other cell phones, from other cells, etc. And we just want this part of the graph because that's where our information is. So again, this is the basic schematic. And as we send the signal that we just showed, we send this into the mixer. And at the mixer, we've got a local oscillator. And the local oscillator is the actual carrier wave producing circuit. And the LC tank, which is basically an inductor and a capacitor in parallel with a cascoded current source, gives us a resonant frequency of 1 over the square root of LC, which we should have all dealt with in our previous classes. VGS, okay, so now that we're actually at the transistor, which is the mixer, VGS is the combination of our DC bias, our band or our baseband signal, and our carrier frequency, V0, VS, and VQ. This is going into the gate of the transistor, which is controlling the output voltage. And this is also tuned, just like the previous inductor capacitor parallel circuit, to create a resonant frequency. And this is also how we filter again. So this transistor is acting as a mixer, as an amplifier, and as a filter. From a electromagnetic standpoint, antennas really detect either the electric field or the magnetic field. if you see either a parallel plate or a dipole, something of that sort, that is generally an electric field receiving or sending antenna. The electromagnetic wave is made up of the electric field and the magnetic field at the same time. However, the way that we receive and create the induction in the antenna changes depending on whether we want, again, the E field or the B field. An antenna array that's more of like a circular loop is going to pick up the magnetic field better than the E field. So here's a demonstration of the E field coming into the dipole. So the E field is hitting broadside on the antenna. So as the sine wave is coming through, this change in the polarization of each of the ends of the dipole creates a movement of charge from the EMF induction. For the B field produced by the change in I, the fields radiate in a circular fashion around and outwards from the dipole. They are also switching signs. So sometimes they're going out and sometimes they're going in, but they're always traveling in an outward direction. All right, that's it for me. Thank you very much.